Let's talk about NumPy. NumPy is the fundamental package for scientific computing with Python. It is a library or package that expands the functionality of core Python. It provides the essential multidimensional array object, ND array, and with it, very efficient storage. It provides functions that can efficiently, which really means fast, operate on this data type. And as opposed to the Python list or dictionary types, data in ND array must be homogeneous. So they all must be of the same type. You cannot have a string and an integer in an ND array or in the same ND array. You only can have all integers or all floats or all strings in one ND array. There's a large infrastructure of Python-based packages that internally use ND array, and to be proficient in its use is necessary to leverage those packages. Sometimes there are some NumPy functions exposed, or you'll get a return value that is an ND array, and to operate on that efficiently, you want to use NumPy and be able to use that. So in short, NumPy is ND array as a data type, plus functions that are built around it, and excellent documentation for all of this on the web. In overview, here, these are figures from the NumPy documentation. Here we have n-dimensional arrays, and the n-dimensional here is not just a simple vector object that you're dealing with, but it can have very high dimensionalities, which is very fast and versatilely implemented. NumPy vectorizes the indexing and broadcasting concepts are de facto standards of array computing. There are a lot of numerical computing tools. This is kind of the functions that I meant, but then there's also random number generators, linear algebra routines, Fourier transforms, etc. So a lot of the tools that you really would like to use to analyze your data are already packaged in NumPy. It's interoperable, so it works on all sorts of hardware, and it's performant. And the reason for that is that at its core, NumPy is really well-written C code. C is a different programming language. It's closer to the machine level where you have to manage memory, etc. NumPy takes care of all of that for you. Easy to use, very high-level syntax, as I said, good documentation, and then also open source. There's an excited community continuing to improve NumPy for all to use for free. The ecosystem around it is vast. These are, again, figures from the NumPy website, but it gives you a broad overview of the fields and the packages that leverage NumPy. So it ranges from quantum computing over statistics, signal processing, all the way to architecture, engineering, some geographic processing, and geoscience, etc. Some other package that we'll look at in this series is Pandas, which is here listed under statistical computing. In geosciences, it's probably worth for you to kind of explore PanGeo, SimPag. OSPI is a package that I use a lot for seismic and geodetic data analysis. On the website, all of these are linked, and you can explore all of these packages, but that should drive home the point that NumPy really is at the foundation of a lot of scientific computing, and it's kind of here to stay. To understand NumPy, you need to kind of get used to the concept of array programming, which captures the operations on arrays or matrices in some intuitive syntax, which is generally closely related to the math that's trying to be expressed. Instead of looping over arrays like we have done so far to perform all of the operations on an element-by-element basis, NumPy efficiently implements these fundamental operations internally. So you can say, NumPy, compute the dot product of these two vectors, and it's going to be doing it for you. There's a function that you can call with those two vectors, and then you get your results back. So you don't have to write the for loop iterating over the elements and then element-wise mush them together in a dot product. This is really important to understand and use because your for loop is always going to be slower than the NumPy implementation, and we'll see that later. What else this does is that it makes very concise and easy to read code. It reduces bugs and enhances reproducibility. Right? It's a very different. Right? It's very different code when you have a few, perhaps even embedded for loops versus a single line with a function that has a name that makes sense, that tells you what it's doing to the operands that it is given. So here is one of those examples. What we have here is we are importing NumPy like we have been, and the function, and what we have here is importing NumPy as NP. So internally, we use NumPy functionality with np dot and then the function, and also the package timeIt. TimeIt allows us to time the runtime of operations. So at first, we generate random data here, 1 million by one entry. So this is a very long vector. It's one-dimensional. And we're using the random number generator capabilities that are implemented in random.rand. And then we have a scalar number here that is 3.0. So this is a float. Okay. And now all we're doing is we're trying to scale the values of, and all we're doing now is we're trying to scale the elements in A by 3, right? So A times 3, a vector by a scalar, is defined as the product of each of the elements in the vector with that scalar. So the naive approach is to write a for loop. We iterate over the length of the vector, and then we multiply each vector element by 3. This really should have been B here. So the naive approach here is to simply iterate over the vector A and multiply its element at I by 3, and then store that back at vector element I in A. And then we stop the first timer, right? So we have a timeIt default timer. We are starting it, and then we have a stop time. And we're doing the same thing again here. We start, and we multiply by B, right? Which is not even requiring a function call, but Python implements the right operation for the asterisk symbol here. So we start the timer, we stop the timer, and then we're comparing the two. So we are printing out here the time for the loop is, some floating point number seconds from stop that gives us the time interval for the first timer, and we do the same thing, start for the second timer, and you can see that the loop takes 1.396 seconds. The NumPy operation takes 0.001, or if you round, 0.002 seconds, which is orders of magnitude difference, kind of trying to drive home this. If you do that operation multiple times in your code, you're substantially slowing things down. Okay, some more basics here. So the way NumPy works is if you want to use it, it needs to be installed within your Python environment. On our AWS setup, that is taken care of for you. So you can always say import NumPy as NP. That's kind of the standard way we do that. Create an ND array by simply saying, okay, data a NumPy array, and we give it a list of value. We have a 4x1. And here are some functions that you could call. Perhaps we want to calculate the sum of the elements of the vector. So on data, we call sum. We'll invoke the function sum on the elements and data and get here 54. We could also calculate the square root. That is a little bit different. That's something to get used to. Not all of the functions are called on the object ND array, here data. Sometimes you have NumPy functions that take this as an input, is the square of these elements. We can also calculate the vector norm, right? That's defined as the square root of the sum of the squared elements. So here we use the linear algebra subpackage of NumPy and tell it to calculate the norm on data, and we get a value here. Some basic matrix operations. Let's again import NumPy as NP. We give our matrix, and we also import pyplot. That's something that you'll learn about in the next few weeks, of the type integer. So we say, hey NumPy, give me an ND array that's full of zeros. It should have the dimensions 512 by 500 types. Hey NumPy, give me a... So we say, hey NumPy, give me an ND array that's full of zeros. It should be 512 by 512 elements, and the data type should be NumPy's data type for integer. Okay, you can find definitions for other data types within NumPy in the NumPy documentation. It's just something that is going to give us a 512 by 512 array with nothing in it. Okay, so now we put something in it. We are saying that data from 50 should be 1. And then we can simply display the data as an image that's within that we imported here. There's a function IAmShow, image show. We'll give it a matrix and it displays it as an image, and we plot it to the screen. And this is what it looks like. We just made a face. This is our matrix, 512 by 512, right? Row 100 through 120, and then 100 through 120 column is all ones. Here's the second